Good morning, everyone. My name is Paramjyot. I am a managing director with Accenture and lead the consulting business for energy clients in India. Honored to be here today in the capacity of the session chair. First of all, a big thank you to the IEW team for hosting us here today. The event is becoming bigger and better every year. It continues to be a pivotal week for energy professionals, not just in India, but worldwide. To now invite Mr. Axel Sommer. He's the Chief Sales and Marketing Officer at Protego. He will explore some explosion protection strategies as a part of his presentation under this domain. Mr. Axel Sommer.
Thank you very much. A very good morning to everyone. I would like to speak about some challenges in Power-to-X applications when it comes to safety issues with hydrogen. And our company Protego is doing research work since the last 70 years in the biggest private-owned testing facility. And I would like to give you some examples what will happen if you are not looking on the good and safe strategy in safety. So what is meant by Power-to-X? The Power-to-X process allows for converting renewable electricity into storable fuels. This transformation technology converts electricity into carbon-neutral synthetic fuels, which can then be used in other sectors or be stored until needed. In addition, the path to net zero requires preventing storage tanks to directly vent to atmosphere. This typically results in more vent headers to be installed in storage tank farms and process units, which are connected to vapor recovery units. The result is a very complex pressure relieving system for which very little guidance is provided in national and international standards. One of the fuels that is generated with the Power-to-X concept is hydrogen. So hydrogen plays a crucial role as a secondary energy carrier, particularly in the chemical industry and refinery industry. Hydrogen is a key raw material in industry, and hydrogen is essential for various processes and high quality products, for example, metal processing, fat hardening, fertilizer production. Hydrogen is also produced as a byproduct in various processes, from crude oil refining process or production of ethane or methanol. So safety devices are used in processes where moderate temperatures and pressure prevail for the chemical industry, manufacturing processes, tank storage facilities. These kind of facilities need a clear, structured safety concept. Hydrogen test chambers for hydrogen power fuel cell vehicles or engine test benches for different car manufacturers. But safety products are also active in special applications like ammonia tank, ammonia as a hydrogen carrier. So what is everything taken into account? For the long-term success of the energy transition and for climate protection, we need alternatives to fossil fuels. Hydrogen will play a key role as a versatile energy carrier. Climate-friendly hydrogen and its derivatives, for example, ammonia and methanol, make it possible to significantly reduce CO2 emissions, especially in industry, power plants, and transportation. In the future, hydrogen and its derivatives should be used primarily where the direct use of electricity from renewable energy sources is sufficient or not possible. But is there anything underestimated? Due to its challenging properties, such as those found in hydrogen, its production, processing, and transport require specialized expertise. Hydrogen has a large explosion range from 4 to 77 volume%. Hydrogen needs a very low ignition energy. Hydrogen has a high diffusion rate. And finally, hydrogen has a very small gap width. It's put into so-called explosion group 2C. So hydrogen requires an extremely high quality of process relevant safety fittings. So the maximum experimental safe gap is the safety-related parameter for the explosive hazard of substances. The risk of explosion increases with rising temperature and rising pressure. The explosion limits shift with increasing temperature and increasing pressure. The explosion range becomes larger. So when you look for an N-hexane or N-propane or ethylene, there is an MESG that is on this level, but there is no high range on volume percentage when you look on this. There is only a small range here from the MESG with a certain safe gap. But when you look on the hydrogen, there is a wide range of volume percentage. So hydrogen is the most critical vapor you can use in your process. So you have to have a clear safety process and safety concept to protect your processes and your plants. So I would like to show you a small video where we made some different explosion tests for different vapors to just give you a feeling about what is the difference between methane, propane, ethylene, and finally hydrogen. So we have a certain pipe length, 1 meter diameter with a plastic bag at the end. We filled the piping with this certain product and we ignite it on one side. And we just want to show you the power of the different explosions when you use different products. So we have a DN1000 piping system. Pipe length is L over D18. And we start with methane, explosion group 2A1. So this is, by the way, a very low explosion. The speed is not very fast. Now we start with propane. Propane is explosion group 2A. You see, it's much faster. Now we go to ethylene, explosion group 2B3. It's even much faster. And now finally we go to hydrogen, explosion group 2C. So hydrogen creates the fastest and the biggest explosion. So when you compare these things, you see hydrogen is starting first. Ethylene, propane, and methane is very, very small explosion with a very low speed. So when you look on the safety in your processes, you always have to be sure to have the right safety concept in your plant by using a certain product. And hydrogen, as you can see in these explosion testings, is the most risky product. But there are also critical factors like process temperatures. So the so-called MESG, the gap width of each product, decreases, gets smaller when the temperature rises up. So when the temperature is higher, the gap size gets smaller, so it gets more critical, the product. The same is with the pressure, the process pressure. When the process pressure increases, the gap size gets smaller and the process will get more critical. So you always have to look on the right safety concept in regard to process conditions like temperature, pressure, surroundings, installation, and use the right safety concept for the right vapor. Otherwise, you might have a big issue in your process plant. We do a lot of testings in our testing facility. And this is one flame arrestor, a big flame arrestor, 2 meters diameter in a pipe system. And this has been certified for a certain approval. But what we also do in our testing facility, we increase pressure or temperature to see where is the limit of these flame arrestors. And when you put a flame arrestor in a piping system where the limit is reached, and you have an installation, like you can see now, it's a piping system, and you install the flame arrestor for an application where the flame arrestor is not tested and certified for, you will see the result. So this is the piping, the flame arrestor is on the right side, and we ignite. The flame arrestor failed and you have a huge damage. And you don't want to have at the end of this piping system your process or your storage tank farm. So these things can happen at the testing facility, no issue, we can do that, we can handle that, but we don't want to see that in your process plant. So therefore we do all these testings. So the incorrectly designed flame arresters have a massive destructive effect. Therefore they must always be tested and approved for the specific application. There is also a big challenge if you have to allow the vapors to get to the atmosphere and you want to protect your tank farm against a so-called continuous burning. This is a typical testing for continuous burning protection. So there is a cover, it's breathing out, there is a melting element, the cover allows to open, and then this flame can burn above the flame arrestor unit without any issues. It's tested for this scenario. It can burn for hours, no issue, because it has been tested for that. This is for normal vapors, for hydrocarbons, like propane, ethylene, methane. But what is about hydrogen? Hydrogen has a much more critical issue on burning scenario. So there are not many protection devices certified and tested for hydrogen. This one is one of the tested devices, but you can imagine that the pressure drop of this device is very, very hard. So whenever you have a certain process, you have to find a safety concept that is sufficient for your safety. So summarize, good safety solutions for the use of hydrogen exist, but for safe operation, a sound safety assessment is essential. Thank you very much. And we have a booth in Hall 2, so for any further questions or detailed questions, we are available at our booth in Hall 2. Thank you very much.
Great, thank you, Axel. I think so. Next we have Vivek Dharmalingam. Vivek is a DGM special projects with Klinger Industrial Products. He'll be covering, a specific topic on zero emission valves for industrial decarbonization through magnetic actuation. So Vivek, over to you.
Good morning and thank you for being here. Before I start, let me start with one sentence which we would like you to remember. What we accept in design, we pay for that in reality. So for the decades, industry has accepted the gland leakage was inevitable, and today we are going to challenge that assumption. So we will present a valve architecture that does not try to detect any leakage after they happen. It removes the leakage path entirely. It's a zero emission by design, using a magnetic actuation to decouple the motion from the containment. We would also like to acknowledge our technology partner, MagDrive Technologies in the United States. So before we talk about the causes, we'd also like to look at the consequences. So what you just saw are the visible consequences of the emissions we rarely see. The valve present in every industrial facility and contributes significant share of the total. Unlike major incidents, these emissions happen quite every day. To understand why these quite emissions matter so much, we'll also need to look at the methane itself. So let's look at why this matters at scale. Methane is not a small problem. Over 20 years of time frame, it's roughly 80 times more potent than carbon dioxide. That makes methane reduction one of the fastest level available for the near-term climatic impact. As a result, regulators and investors are focusing heavily on methane intensity, and industry is being asked to respond. So where do these emissions come from inside facilities? Let's have a look. Globally, the large volume of emissions lost every day, it represents tens of billions of lost product every year. When the emissions are broken down at the component level, the valves are consistently among the largest contributors, often cited up to 60% in many facilities. This is not an accidental, it reflects a long-standing design pattern. The impact is not an abstract, it shows up a real measurable losses. So let's put number on that. Each year, the industry is estimated to lose between 3.6 to 4 trillion cubic feet of natural gas, around 30 billion US dollars in the product value that never reaches the market. These losses are often invisible on the balance sheets, but very real for the operators and for the climate. Methane climate behavior makes those losses urgent. Methane is short-lived but extremely powerful. Cutting now reduces the near-term global warming quickly. This is why the government, OGCI, EPA, European Union, industry initiatives are prioritizing the methane reduction. It delivers the fast and measurable results. To reduce the methane emissions, first we have to understand why it leaks. Let's have a look. When we trace fugitive emissions to their root cause, the valve stem and its sealing solutions dominate. The packing is a dynamic seal. It rubs, it compresses, it relaxes, and it ages. In addition to that, thermal cycling, vibration, and corrosion all drive progressive degradation. Critically, the first two packing rings that carries most of the sealing load, and they are the first to fail. This is not a simple maintenance issue, it's a physical consequence of the sealing motion. So industry has tried several ways to address this, so let's review them. Over the time, the industry has tried three main approaches: pack stems, bellows, and diaphragms. The pack stem trade for the friction, bellows removes the friction but introduces a flexual fatigue. Diaphragm works in some services, but the creep and fatigue in others. So all three relies on moving, flexing elements inside the pressure boundary, and that moves creates a flex failure mechanism over the time. This brings us a real design challenge. The fundamental challenge is geometric. As long as motion crosses the pressure boundary, the leakage path is unavoidable. This leads to a different question. Instead of pursuing a better packing, can we separate a motion from the containment altogether? The question leads to a different approach. The idea is straightforward in the concept. Remove the dynamic seal. Insert the moving internals inside a solid, static metallic pressure boundary and transmit the torque without penetrating that pressure boundary. When the pack stem is never exposed to the atmosphere, there is no leakage path. This is a leakage path elimination by design. Let's look at what the architecture actually look like. The architecture has three defining characteristics: no stem penetration, no packing, and no dynamic sealing interface. The pressure boundary is static, actuation is external. This is not an incremental improvement to a packed valve, it represents a different class of the valve. This is easy to see visually. This is the conventional valve with the stem penetrating the pressure boundary. This is a hermetic design, sealed chamber. The torque transmitted magnetically through the valve. same function at the port, but different containment philosophy. The key enabler here is magnetic actuation. Torque is transmitted using a radially aligned permanent magnets across the static wall. There is no shaft penetration, no dynamic packing, no mechanical contact across the pressure boundary. The motion synchronized and rotationally controlled and allowing reliable actuation, leaving the containment undisturbed. The static pressure boundary is where the real reliability comes from. Because the containment is static, it behaves structurally like a pressure vessel. There is no flexing, no cyclic strain, no rubbing, no fatigue at the sealing interface. The failure mode that limits metallic bellows and the diaphragms simply does not exist here. The result is permanent containment integrity. But the architecture alone is not enough, it has to be proven. The design was subjected to internationally recognized tests. We have conducted APA 6FA5 test, followed by ISO 15848, APA 624, 641, the fugitive emission protocols, endurance and tightness testing, and also we have conducted cryogenic and multi-gas trials in NASA. All testings were conducted in third-party laboratories in the United States, which is globally recognized under defined standards and conditions. So what were the results? Across the mechanical cycling and the thermal exposure, fire testing and cryogenic multi-gas trials, the valves reported no detectable leakage within the limits of the applied global test methods. Helium mass spectrometer testing measured leakage below the stringent detection levels. The results demonstrate that eliminating the leakage path is achievable under demanding conditions. The performance opened the door for extreme service conditions. The concept operates from deep cryogenic service through the fire exposure conditions. The magnetic coupling remains stable at the low temperatures, and in some magnet grades, coupling strength actually increases the temperature drops. The static pressure boundary eliminates the need for extended bonnets, simplifying the cryogenic installations, which is particularly important for hydrogen and LNG. The hydrogen services places the highest demand on containment integrity, permutation, boil off, recompression loss matter, removing the dynamic seal, removing the leakage pathway and the maintenance. The result is improved containment, reliability and operating efficiency in hydrogen and LNG systems. So where does these deliver most value in the practice? The high value applications include high cycle valve applications, LDR intensive facilities, hydrogen and LNG systems. The valves located in hazardous or difficult to access areas, you don't need to replace every valve you see to see a meaningful gains. You prioritize the valve leakage is more costly or more risky. This also changes how we think about LDAR. Today, the LDR is largely reactive, find the leak and fix the leak. The valves demonstrated non-detectable emissions under acceptable standards. The operator can reduce routine LDR monitoring scope for these components subjected to policy and regulatory engagement. This shifts the resources from constant inspection to preventive engineering. And this has a real regulatory implications. The result is fewer monitored components, low inspection frequency, simpler documentation, and reduced audit exposure. When the valve is demonstrated non-detectable emissions under acceptable standards, it becomes easier to justify reduced LDAR scope with the regulator agreement. This is compliance by design. This is not compliance by the paperwork. So now let's look at the business case. Upfront, capex can be higher than the low-cost packed valve, but in the emission-regulated assets, OPEX dominates the packing replacement, such as LDAR, labor, unplanned downtime, product losses. Removing the leakage path converts recurring operational expenses in one-time technical investment. So this is where the life cycle thinking matters. The traditional L1 procurement optimized for the upfront price, the T1 procurement optimized for the technical performance and the life cycle outcomes. Moving from L1 to T1, deploying a zero emission valves selectively can reduce the total cost of ownership by 30 to 40% in many applications, depending on duty cycle and operating conditions, and the emission impact is direct. Replacing roughly 100 conventional valves can avoid order of 200 tons of carbon dioxide equivalent emissions per year, depending on the application and baseline leakage. This is direct scope 1 reduction, prevented emissions that are auditable and persistent over its asset life. This feeds straight into the hydrogen economics. Containment integrity improves yield, reduces decompression, boil-off losses, and increases the uptime. In hydrogen systems that directly reduce the levelized cost of the hydrogen, containment is not just a safety issue, it's an economic lever. Let's summarize the architecture in one slide. External actuation, internal static containment. Magnetic torque transmission, no dynamic seals. The valve becomes permanent containment rather than a recurring maintenance item. That fundamentally redefines the valve role in the plant. Finally, let's connect to the India's priorities. The architecture supports objectives under India's green hydrogen mission and the methane intensity reduction targets. It enables industrial systems that are productive, export competitive, and the low emission, and supporting a long-term decarbonization goals. So before we close this, one final insight. For the decades, industry has accepted the gland leakage was inevitable. We invested in better packing, better detection methods, more inspections, but very rarely question the underlying assumption. When the containment is designed to be static, the zero leak is no longer an aspiration. It becomes a default condition. With that, thank you for your attention and thank you for your time. The technology is ready for the field demonstration at scale. If your organization is evaluating the next generation containment strategies, we welcome a conversation, particularly LDR intensive facilities, hydrogen hubs, and high value cryogenic services. We will be at the booth 1D02 and look forward for the discussing the standards, deployment pathways, and the pilot programs. Anyone can fail, but the environment cannot afford that failure. Thank you.
Next, we have Manjush Ganiger. Manjush is a hydrogen utilization platform manager at Baker Hughes. Manjush will be presenting, on the topic of valorizing flare gas into low carbon liquid fuels. Manjush, over to you.
Thank you, Session Chair, and good morning, everyone. So today we would like to talk about our integrated engineering solution for conversion or valorization of flare gas into low carbon liquid fuels. So as mentioned by the previous speakers, the oil and gas industry has seen flare gas as one of the most pressing pain point, and here we are with a solution with which the oil and gas customers can valorize that flare gas and convert them into a high grade, high energy intensity valuable chemicals like gasoline or jet fuel. So to give a bit of a background about who we are as a company, Baker Hughes is an energy technology company with a focus in making energy safer, cleaner, and more efficient for people and the planet. We are predominantly known for our oil field service and equipment business, but we do have a big chunk of business that is focused on, a turbo machinery and equipment business, where we provide compressors and gas turbine for oil and gas sectors, as well as new energy solutions businesses. In 2024, we made roughly about $28 billion in revenue, and we are present across more than 120 countries. So yeah, that's about our company in brief. To quickly touch upon how we are serving the new energy solutions. So we do have a specific business that is focused on that, which we call it as climate technology solutions business, with which we cover on the portfolio of hydrogen, CCUS, clean power, as well as emission abatement. So just to quickly touch upon, on hydrogen side, we do provide hydrogen-based gas turbines that are capable of burning 100% hydrogen, as well as hydrogen compression solution for green ammonia or methanol kind of hydrogen derivative production as well. Similarly, on CCUS side, we play across the value chain of CO2, so right from the capturing to storage and transportation, and until the utilization as well, where we provide solutions for CO2 compression, storage, and on biomethanation for the utilization part. Finally, on the emission abatement, so we are the company that provide technology solutions as well as advisory services for flare gas handling systems, that is deflaring solutions to support the decarbonization of traditional oil and gas sectors. So with that, just to also mention about emission reduction potential, what we should all focus on, because to achieve net zero by 2050, it is essential that more than 45% of the emissions have to be reduced within this decade. And this is the numbers coming from various agencies across the globe. And when we talk about emissions, the methane emissions play a critical role as well. So mitigating methane emissions is important, which predominantly goes into the atmosphere through either vents and flares and etc. So what are the emissions we are talking about? When it comes to the flare gas related release to the atmosphere. So generally, the flaring is a major emission source in the oil and gas sector, where during the oil extraction, let's say, there would be a lot of associated gas, which is very rich in calorific value, that generally gets flared and releases CO2 to the atmosphere. The other type is the venting, where the unignited waste gas or off gas from the different industries is released. This could be because of, let's say, by the design or due to malfunction in the process, it can happen, and it is invisible to the naked eye, but it can definitely be felt through the climate change as well. On the fugitive emission, which is more of a unintentional release of gases to the atmosphere, mainly the hydrocarbons, which could be due to the flaws in the design or inefficient equipment or very age-old infrastructure also. And then there are combustion-related emissions, where the flare gases, if combusted, or if let's say if combusted in a gas engine or gas turbine, that release additional CO2 emissions as well. So this is just a background about where we play as a Baker Hughes, from the upstream oil, offshore and onshore drilling to midstream for LNG storage, transportation, as well as in refinery and petrochemical sectors. So in terms of the solution, what we provide on the flare gas utilization, so specific to customers based on the economic feasibility, the environmental regulations, as well as how potentially we can integrate the system into the existing system. So we look at solution based on the composition of the flare gas and the impurities present, as well as the flow rate of the gas itself. For example, some of our key technologies are flare to power conversion, because in some cases, when the flare gas is having a very high calorific value, we generally provide a solution where that flare gas could be combusted in our gas turbines to produce power, which is less greenhouse gas emitting solution compared to direct venting of the flare gas to the atmosphere. And also in some cases, when the flare gas is already pure enough or it has a very uniform composition, we could also use compressors to compress the flare gas and re-inject them in the pipeline to repurpose it for the downstream application. And we also support in the recovery of the liquids, natural gas liquids, C2, C3 and C5. This will provide a greater value for the customers when they recover these high grade molecules like LPG or propane, and then they can be reused as an additional revenue stream. And finally, the flare to liquid, which is a topic of interest for today's discussion. So we have come up with a solution where the flare gases can be converted into a high energy density molecules or the liquid fuels which are low in carbon intensity, because the liquids what we are talking about is methanol or jet fuel or even the gasoline and LPG. So to deep dive into the solution what we are talking about, so the flare gas could contain anywhere between 50 to 100% of methane or C2 to C4 in the range up to 50%, and remaining could be CO2, CO or N2 kind of elements. So we have come up with a solution where the flare gas can be first converted into syngas using the existing reforming technologies, and then convert syngas into methanol, which could be used as a final product for the many of the chemical plants, or methanol could also be further used as an intermediate to upgrade it into either LPG and gasoline or as a jet fuel. So this unlocks a greater revenue stream for the customers, and it provides the decarbonization for the flare gas utilization. So this solution, because before looking into this solution, when we were interacting with many oil and gas customers, what we learned from them is that most of the refineries or the upstream plants are very remotely located, and flares are generally is vented to the atmospheres, and there is no grid connection. So customers were looking for solution which are self-sustaining as well as containerized to make them modular, because the flare gas flow rate changes a lot. So in order to counter to all these requirements, we came up with a solution which is modular and skid mounted. So it can switch on and off in terms of what is the flow rate of flare that is coming out, and also it can be very much self-sustainable, not depend on any external grid connectivity. So we allow for converting this flare gas into these low carbon liquid fuels. Now this solution is even more interesting because there are a lot of regulatory systems worldwide that provide carbon incentives for converting waste gases like flare gas into a very high grade molecules. So some of the low carbon frameworks that exist worldwide are, for example, in Canada, there is clean fuel regulation, which provides the incentives for producing low carbon liquid fuels. And there are a couple of them in US as well. And in Europe, there is European Union RED 2 and RED 3, as well as Fuel EU maritime kind of regulatory systems. And these are the compliance market systems that attract, that provide a greater carbon incentives in order to bridge the gap between the cost of producing low carbon liquid fuels from the process that I just talked about compared to the fossil based liquid fuel production pathways. So those were the one type of compliance market regulatory systems, but there are also other pathways. For example, there are avoided flared emissions, because by using the waste gas like flare gas into producing these liquid fuels, we are avoiding those emissions at the site. So this kind of solution also attracts the carbon incentives from avoided emissions point of view. And there are also independent certification schemes that can boost the business case of producing these kind of liquid fuels as well. So now, very quickly, let me now give some of the use cases in terms of comparing different flare gas or deflaring solutions. For example, if we go for direct venting, which is a base case number one, uh, considering a case of 5 million scaf per day of flare gas with composition that consists mainly 95% hydrocarbon and remaining to be nitrogen and CO2. So when we try to directly vent it into the atmosphere, the CO2 emission would be somewhere in the range of 2.5 million kg CO2 equivalent per day. So this is with the direct venting, which is currently the base case. The another base case could be that we flare that 5 million scaf per day of flare gas, we combust it and release the CO2 to the atmosphere. And of course, when we compare this case with the previous one, where there is a direct methane emission, so as we know, methane has a higher greenhouse gas potential compared to the CO2. So the net CO2 equivalent emission has now come down for this case, which is about roughly 433,000 kg CO2 equivalent per day. But in order to cut down these emissions, the case 3 could be that we convert flare gas into power using the gas turbines. So as I mentioned, we have NoILT 16 gas turbine, which is a 16 megawatt simple cycle gas turbine with efficiency of about 35%. It can consume the flare gas in the range of 2 to 20 million scaf per day with a typical unit of 4 million scaf per day of fuel. So when we directly combust the fuel, the flare gas into the gas turbine and then do the carbon capture in the downstream, we see a significant reduction in the total CO2 savings. For example, with respect to venting, we will see 130% CO2 emission saving versus flaring, it will be 280% savings in the total CO2 emissions. And finally, okay, the case number 4 is more of having also a direct air capture, because all the industries that produce the flare gas are remotely located, but at the same time, there is also a direct air capture that can capture the CO2 directly from the air, but it requires a lot of power and they are also remotely located. So why not we connect both of these? That is by converting flare to power using gas turbines and then provide the power to the direct air capture that can additionally remove the CO2 from the air directly. So when we look at that kind of a solution, we see that apart from venting and flaring, we do see additional CO2 saving or CO2 capturing of about 101 kilotons per annum. So by this, what we are doing is the flare gas, which was completely a waste and it was giving a lot of CO2 emissions to the environment, we transform that into power, and from power we have now driven a direct air capture unit that will further bring down the CO2 emission for us. And finally, if we compare the CO2 emission saving with the flare to liquid pathway, so in this case again the flare gas, which was very wasteful, or it was not getting fully utilized, so now when we convert that into methanol, we do see a savings in both venting, with respect to venting and flaring, and we will also attract additional incentives from different regulatory systems that are there worldwide as well. So, and also the liquid fuel what will be produced can be directly used as a drop-in fuel in the downstream. So that will so these kind of low carbon fuels will directly replace the fossil-based liquid fuels that would otherwise be produced. So when we look at the entire CO2 emissions for the entire chain, we will see that for every megajoule of fuel produced, it will offset about 45 or 46 grams of CO2 equivalent in the downstream as well. So with that, what I would like to say is that the flare gases, which were the source of emissions, are now being transformed into high-grade molecules in a more economical way, and this is being supported by rapidly evolving regulatory landscape. So this can unlock a greater potential for revenue generation as well as decarbonization for our traditional oil and gas customers. So thank you very much, and we look forward to discussing if there are any questions after this session. So thank you for the opportunity.
Thank you so much, Manjush.
Thank you.
Okay, we'll move on to the next presentation. We have Suyog Gawande. Uh, Suyog is in AGM with EIL, and he'll be, sharing his perspective on green steel. So Suyog, over to you.
Hello. Good morning, everyone. Hope I am clear and loud so that everyone can understand. This presentation is just for a 15 minutes. In 15 minutes, it is not possible to explain all the things, but I will cover majority things which are important and why Indian government has spent more than 20,000 crores as an initiative for and incentives for the steel manufacturers in India. So this is the green steel. What is green steel? I will cover in this presentation the importance of this green steel. First, I will introduce the presentation and what are the steps, in which step this presentation will be carried forward. Before moving to the green steel production, I will just cover overview of the normal conventional methods of the steel productions. Then what are the environmental impacts of the conventional steel manufacturing? Then what is green steel? And what are the methods by which we can produce the green steel? And comparison of the normal conventional steel against the green steel. Why to use the green steel? Targeted sectors and utilizations of this new steel. Then challenges we are facing for the production of the green steel. Pros and cons. Major global initiatives which are already taken up globally, as a majority of the European and North American companies has already initiated the this green steel production. Then existing government policies and the initiatives which are being taken up in India. Way forward and conclusion. Let's start with the introduction. Here everyone is here and talking about the reduction of the carbon emission in the environment. But see, steel industry contributes almost 7 to 9% of the global CO2 emission in environment, and green steel production aims to drastically reduce that carbon footprint in the environment. Then what is green steel? Green steel is a low carbon steel produced using the renewable energy or hydrogen instead of coal and the fossil fuels. Why this is needed for the India? Because India is a developing country, and almost 50% of this steel is being used in the infrastructure projects, and almost 40%, around 40% steel is being used in the oil and gas sectors. Indian steel sector is the second largest emitter of the CO2 in the environment after power generation. Then we will move to the conventional methods of the steel production. Basically, steel is being produced in the basic oxygen furnace, where coal and coke is used to generate the heat and create the molten metal for steel production. This method emits almost 2 metric tons of CO2 for the production of 1 metric ton of steel in basic oxygen furnace. And in electric arc furnace, means pure electric arc furnace, there is no renewable energy source or hydrogen is used in the pure electric arc furnace, where we can see it emits almost 1.5 to 2 tons of CO2 for the production of 1 ton of steel. Then this CO2 emitted in the environment, what are the effects? Carbon emission and the climate change. Average CO2 emission of 1.5 to 2 metric tons for the production of 1 single ton of steel releases the methane during the coal mining and the carbonization, which is a significantly more potent as a warming agent. During the steel production, there is a conventional steel production method. There are some particulates released in the air during the sintering and the smelting. That is very harmful to the respiratory system of the human body. Some toxic components like naphthalene, ammonium compound and the sulfur dioxide is also released in the environment, which is the main important reason for the acid rain, and it is also carcinogenic. Majority of the water consumptions for the conventional steel is being released in the rivers and the oceans that contaminates the ocean and the other water sources. And solid weight generation is the major constraint which is impacting this conventional steel production method. Then what is green steel? In green steel, the methods of production is different because we are not using here coal or the fossil fuels to generate the heat. Main approach for the production of the green steel is, instead of using the coal and the fossil fuel, we use the hydrogen gas, which is produced by the use of renewable sources like solar and wind energy. These are some methods of production of the green steel. This is just schematic representation. In black line arrow is a conventional method of production of the conventional steel, where iron ore is taken and it is heated by the temperature created by the fossil fluid and the coal or charcoal. However, in the red line direction reduction, which is shown in the red line, you will see that solar energy or the wind energy is used to electrolyze the water and separate the hydrogen and water. This preheated hydrogen is used along with a natural gas and used to melt the metal and produce the steel. Here you can see the drastic reduction of the CO2 emission in the environment. It is almost 0.7 to 0.9 metric tons per 1 ton steel production. This is being used widely in the Europe and the North American countries. If we compare the conventional steel produced by the basic oxygen furnace and the steel produced with the use of renewable energy sources, there is no major difference. Almost tensile and mechanical properties are same. However, to get the required thickness, we have to be more properly process the steel production. Then why to use the green steel? As our nation goal is to have a net zero target by 2070, Indian target is there, and EL target is by 2035. Then long-term benefits of the green steel production is carbon credits. As you know, the Reliance industry has already prepared one forest, one Tara, that is for the green credit and initiatives to get from the government. What is the market readiness? As of now, in India, SAIL, Tata Steel and Jindal Saw has already established the pilot plants to produce the 100% green steel from the renewable energy sources. What are the target sectors to use the green steel are oil and gas sector and metro, like infrastructures like metro, national highways, railways, smart city mission, housing, greenfield like airports and ports. And we expect by 2023, 2030, the demand of the steel will be by 130 million tons of the steel. And if we use almost 25% of the green steel, then we can save the 100 millions of the CO2 emission in the environment. If green steel is that much beneficial, then why everybody is not manufacturing green steel? There are some challenges. There are two major challenges we will discuss here, which is the economic challenges and the technological challenges. In economical challenges, we can see the green steel is being produced with the use of the hydrogen, means electrolyzing to be done to separate the hydrogen and oxygen from the water, which is very much expensive as of now. With the current technology, it is expensive. It is almost 0.1% of the global production, and its cost is 5 times higher than the fossil based hydrogen production. Also, this uh, electric arc furnace using the hydrogen base as needs the electrodes, which is being manufactured by the graphite. And as we know, there is a high demand of the EV, electric vehicles, and less supply of the graphite. Also, there are many industries, means steel producing industries, they have already established and modified their plants, which can run for the 20 to 40 years of the lifespan. And retiring that plant too early to create the green steel will have the drastic and significant impact on that financial conditions. There are some regulatory challenges also there, and market uncertainty. Shifting the trade policies will impact the green steel production also. And if we talk about the technological challenges, major challenge is for the production of the hydrogen, because for producing the hydrogen we need the large infrastructure of the renewable sources. As we know that EIL also diversified in the different sectors like solar, wind, and nuclear. This hydrogen EIL will play the major critical crucial role for the nation development, and this hydrogen will be produced at a much cheaper rate in future. And also the quality of the iron for production of the green steel needs somewhat higher as compared to the conventional steel. Technological challenges also will be reduced with the increasing technology and scaling up the green hydrogen production and transportation of hydrogen. What are the pros and cons of the green steel? It will be divided into short and long terms. If we talk about the short term pros, it will have very low carbon footprint on the environment. Then ESG credibility and early mover advantages will have the advantage of a green certification, means that manufacturer or steel producer will migrate to the green production, will have the advantage of the green certification and some incentives from the government. What are the short term cons are? High initial cost, as we discussed, high initial cost for the establishment of the renewable sources like solar and wind farms. Then limited domestic availability. As of now, there are very less suppliers, which are majority are overseas suppliers, which are producing the green steel. Indian suppliers and major steel giants have already established these pilot plants, and they will start the producing 100% green steel by end of 26. And one major con is lack of mandatory usage policy. As of now, government has already promoted, but there should be some policies which regulates the steel production in India. If we talk about the long-term goals or pros and cons, it is aligning with the nation goal for the net zero by 2070. The resilience to the future carbon taxes. Then it will be cheaper with the technology and the scale of renewable sources. If we talk about the long-term cons, technology is still maturing, and policy support from the government needs to be improved and evolved. Major global initiatives which are taken in the Europe countries are in Sweden, some suppliers like Stegra and Hybrid already producing 100% green steel. In China also, the giant of steel giant in China, HBIS group has already started producing 100% green steel. Similarly, in India, ArcelorMittal, Tata Steel, JSW and POSCO has established the pilot projects. Existing government policies and initiatives are like carbon border adjustment mechanism and carbon pricing and trade schemes. Indian government has already invested almost 20,000 crore for the as a incentives for the green hydrogen steel production. And one more thing is that green steel is produced from the scrap also. It is also green steel. We can take, consider it as a green steel. Some national policies which promotes the green steel production are established from 2017 onwards, and MOU is also signed between the SAIL, Tata Steel and JSW. If you go way forward with this presentation, collaboration between the industry, government and the steel users, means end user, will make it possible for the Green India to produce the 100% green steel in the future. We need the green financing and the public-private partnership. Then transition roadmap, it is a transition roadmap for the net zero 2070 mission of India. Some policy recommendations are, there should be a mandatory green steel percentage to be mentioned in the tenders, government tenders specifically. If we consider 10% of the minimum green steel to be used for the production of the government project, then it will be automatically promoted and we can get the local steel producers also. Then technological roadmap is, we need to scale up the hydrogen hub and hydrogen production and the storage and transportation. And we should promote the R&D and funding through CSIR. In conclusion, I will say green steel is have a vital role for the sustainable industrial future, and with the public and private collaboration, we can achieve the 100% green India. Green steel is a backbone of a net zero world. Thank you.
Thank you all, and thank you for being here today.